solar-powered artificial leaf, the future of clean energy. Human civilization stands at a pivotal moment in its energy history. For over a century, global development has been tightly coupled with the extraction and consumption of fossil fuels, coal, oil, and natural gas, which have fueled industrialization, transportation, and technological progress. However, these same fuels are also the primary drivers of climate change, air pollution, and ecological degradation. As nations grapple with rising carbon dioxide levels and the urgent need to transition toward sustainable systems, scientists are increasingly looking to nature for clues. Among nature's most elegant and powerful processes is photosynthesis, the mechanism by which plants convert sunlight, water, and carbon dioxide into energy-rich organic molecules. Inspired by this natural blueprint, researchers have conceptualized and developed the solar-powered artificial leaf, a device that uses sunlight to generate clean fuels in an environmentally friendly manner. The artificial leaf is not merely a scientific curiosity, it represents a profound technological innovation with the potential to redefine energy production, carbon capture, and sustainable fuel generation. Unlike traditional photovoltaic solar panels that generate electricity, the artificial leaf uses sunlight to create chemical fuels, which can be stored, transported, and used on demand. This ability to store solar energy in a stable chemical form offers a solution to one of renewable energy's most persistent challenges, intermittency. This essay provides a comprehensive exploration of the solar-powered artificial leaf, examining its scientific foundations, design principles, technological advancements, potential applications, challenges, and future prospects. By understanding this emerging technology, we gain insight into how nature-inspired engineering could become a cornerstone of a future carbon-neutral energy economy. Photosynthesis, the natural blueprint. The essence of natural photosynthesis. Photosynthesis is the process by which green plants, algae, and certain bacteria transform light energy into chemical energy. Using chlorophyll and other pigments, plants absorb sunlight and use it to drive the conversion of water and carbon dioxide into glucose, a chemical fuel. This reaction has sustained life on Earth for billions of years. Yet, natural photosynthesis operates at an energy efficiency of only about 1 to 2%. Plants are optimized not for energy production but for survival, reproduction, and ecological interaction. Humanity, however, needs far greater efficiency to meet the world's energy demands. Learning from nature without copying it. The goal of artificial photosynthesis is not to perfectly reproduce nature but to learn from its principles and engineer a system that uses sunlight to generate useful fuels at higher efficiency. Instead of producing glucose, artificial leaves typically aim to produce hydrogen, H2. Carbon-based fuels, such as methanol or carbon monoxide. Syngas, a mixture of carbon monoxide and H2 used industrially. By using more efficient materials and catalysts than those found in nature, artificial photosynthesis can potentially surpass biological efficiency while preserving sustainability. The artificial leaf concept. What is a solar-powered artificial leaf? A solar-powered artificial leaf is a synthetic device that mimics key components of photosynthesis. It uses a semiconductor, similar to those in solar panels, to capture sunlight and catalysts to drive chemical reactions. The output is a clean, storable fuel created directly from water and carbon dioxide. While designs vary, most artificial leaves aim to achieve sunlight absorption, water oxidation, to produce oxygen and hydrogen ions, fuel-forming reactions like hydrogen generation or carbon dioxide reduction. The device operates autonomously using sunlight as its only energy input, no external electricity needed. Core components of the artificial leaf. Most artificial leaves include photoabsorber, semiconductor. This layer captures solar energy and creates electron, hole pairs. Materials used include silicon, gallium phosphide, perovskite semiconductors, bismuth vanadate. Catalysts. Catalysts speed up the chemical reactions necessary to split water or reduce carbon dioxide. Hydrogen evolution catalysts, platinum, molybdenum sulfide. Oxygen evolution catalysts, cobalt phosphate, nickel iron oxides. Carbon dioxide reduction catalysts, copper, silver, cobalt complexes. Electrodes and membranes. Electrodes transport electrons while membranes prevent gases from mixing. Support structure. Some modern designs allow the device to float on water, increasing scalability and reducing land use. Mechanism of operation. Water splitting. The primary function of many artificial leaves is water splitting, where water molecules are broken down into hydrogen and oxygen. This involves two half reactions. Oxygen evolution reaction. Hydrogen evolution reaction. Hydrogen produced this way is a carbon-free, renewable fuel. Carbon dioxide reduction. More advanced artificial leaves can reduce carbon dioxide into useful hydrocarbons. These reactions create fuels that can be used in existing engines and industrial systems, making artificial leaves compatible with today's energy infrastructure. Historical evolution. 1970s, foundational discoveries. The origins of artificial photosynthesis trace back to the Honda, Fukushima effect, 1972, which demonstrated that titanium dioxide electrodes could split water under UV light. This discovery opened the door to using semiconductors for solar-to-fuel conversion. 2000 to 2010, major advances in materials. Developments in semiconductor science, nanotechnology, and catalysis paved the way for integrated artificial leaf systems. 2011, the Harvard artificial leaf. Daniel Nocera's team introduced the world's first practical, integrated artificial leaf using a silicon photoabsorber and cobalt phosphate catalyst. It operated in regular water and sunlight, marking a breakthrough in performance and environmental compatibility. 2019 to present, floating and carbon dioxide reducing leaves. Researchers at Cambridge developed an artificial leaf that could float on water and convert carbon dioxide from the air directly into syngas. This innovation has opened new possibilities for scalable deployment. Key materials and engineering innovations. Semiconductor photoabsorbers. An ideal photoabsorber must absorb a broad spectrum of sunlight, generate and transport charge efficiently, resist corrosion in water. Perovskite-based photoabsorbers have gained attention because of their high absorption efficiency, although stability remains a concern. Catalysts. Catalysts determine the device's efficiency and cost. Platinum. The best hydrogen evolution catalyst but expensive and scarce. Cobalt phosphate. A promising oxygen evolution catalyst used in the Harvard leaf. Earth-abundant alternatives. Nickel iron oxides and molybdenum sulfide offer lower cost while maintaining reasonable performance. Membranes. Proton exchange membranes, example NAFEN, help separate gases and transport ions but add cost and complexity. System integration. Bringing all components together into a compact, functional system requires precise engineering. Efficient charge separation. Water management. Gas collection. Long-term stability. Integration challenges remain one of the field's biggest obstacles. Advantages of the artificial leaf. Environmentally sustainable fuel production. Artificial leaves turn abundant natural input sunlight, water, and carbon dioxide into clean fuels without producing harmful pollutants. Solar energy storage. Chemical fuels like hydrogen and methanol provide a way to store solar energy for use at night or during cloudy periods, overcoming intermittency issues inherent in wind and solar power. Carbon neutral or carbon negative operation. By consuming carbon dioxide, artificial leaves can contribute to carbon reduction. If the produced fuels are burned, the net effect can still be carbon neutral. Off-grid potential. Artificial leaves can operate anywhere sunlight and water are available. This makes them particularly promising for Rural electrification. Remote or resource-poor regions. Disaster relief applications. Compatibility with existing fuel infrastructure. Hydrogen or methanol produced by artificial leaves can be used in fuel cells, internal combustion engines, chemical manufacturing. This avoids the need for immediate infrastructure overhaul. Challenges facing artificial leaf technology. Efficiency limitations. Most existing artificial leaf systems achieve efficiencies between 5 to 15%. For widespread adoption, efficiencies closer to 20 to 25% may be needed. Material durability. Exposure to sunlight and water leads to degradation of semiconductors and catalysts. Designing long-lasting materials is essential. High costs. The use of rare materials like platinum or iridium increases costs. Scalable, inexpensive alternatives are required. Product selectivity in carbon dioxide reduction. Carbon dioxide can be converted into many different products. Controlling the reaction toward a single desired fuel is difficult and requires advanced catalyst design. System scalability. Producing laboratory devices is relatively easy. Scaling to square kilometers of production requires major breakthroughs in engineering, manufacturing, and maintenance. Current research trends. Multi-junction photoabsorbers. These systems stack semiconductors tuned to different wavelengths of sunlight, boosting overall efficiency. Floating artificial leaves. Floating devices can be deployed on lakes, reservoirs, or coastlines without competing for land. They also stay cooler, improving performance. Biohybrid systems. Some researchers are combining artificial systems with living organisms such as bacteria that naturally process carbon dioxide. These hybrids could produce a wider range of fuels. Perovskite-based leaves. Perovskites offer high efficiency and low manufacturing costs. Current research focuses on improving stability in outdoor environments. Integrated capture and convert systems. New designs can draw carbon dioxide directly from the air, eliminating the need for concentrated carbon dioxide inputs. Applications and real-world potential. Green hydrogen production. Hydrogen is central to many visions of a green energy future. Artificial leaves could become a major source of renewable hydrogen for fuel cell vehicles. Steel production. Ammonia synthesis. Grid-scale energy storage. Carbon capture and utilization. Artificial leaves can convert atmospheric carbon dioxide into fuels and chemicals, helping reduce global carbon levels. Agriculture and rural energy. Portable artificial leaf systems could power irrigation pumps, greenhouses, and off-grid farming tools. Water treatment and environmental management. Artificial leaves also produce oxygen, which could aid aeration in natural lakes or wastewater treatment plants. Space exploration. In future long-term space missions, artificial photosynthesis could generate oxygen and fuel from sunlight and water on the Moon or Mars. Economic and environmental impact. Economic potential. If artificial leaves become commercially viable, they could reduce reliance on fossil fuels, create new industries in solar fuel production, lower the cost of hydrogen and synthetic fuels, stimulate job growth in green technology sectors. Environmental benefits. Widespread deployment could reduce greenhouse gas emissions, remove carbon dioxide from the atmosphere, improve air quality, mitigate climate change impacts. Life cycle analysis, however, is needed to ensure the materials and manufacturing processes are environmentally sustainable. Future outlook. The solar-powered artificial leaf remains in a developmental stage, but progress over the last decade has been remarkable. Key priorities for the future include increasing solar-to-fuel efficiency, enhancing system durability, reducing costs through abundant materials, scaling up manufacturing, integrating artificial leaves with existing energy networks. With continued research, artificial leaves may become as common as solar panels are today, generating clean fuel directly from sunlight, water, and air. Conclusion: the solar-powered artificial leaf is a visionary technology that merges the elegance of natural photosynthesis with the power of modern materials science. By harnessing sunlight to create storable, carbon-neutral fuels, artificial leaves offer a promising solution to some of humanity's most pressing challenges: climate change, energy insecurity, and environmental degradation. Although significant hurdles remain, particularly in efficiency, cost, and scalability, the field is advancing rapidly. As researchers refine photoabsorbers, catalysts, and integrated systems, the artificial leaf may soon transform from laboratory prototype to global energy asset. In an era where sustainable solutions are urgently needed, the artificial leaf stands as a remarkable example of how learning from nature can lead to technologies capable of powering a cleaner, more resilient, and more equitable future.